So we are going to understand electric flux now. So let us try to understand this word. Flux means related to flow, and electric here indicates electric field. So we are trying to somehow measure the quantity of field lines or the amount of or the number of field lines that are crossing some given area. So in order to understand this, let's go back to class 11th and relate this to the flow of a fluid through a cross-sectional area. Let's say we have this window. Let's say this is 2 meters square. This is the area. And imagine if we have a fluid that is flowing out of this window, and the speed or velocity of the fluid is 10 meter per second towards right. So this is essentially the velocity. Now, here 10 meter per second would mean that the fluid should be able to cover 10 meter every second. So imagine if we have to calculate the quantity of fluid that is flowing out of the window in 1 second. Quantity of flow. So let's say in 1 second, the fluid has been able to cross 10 meter like this. And the cross-sectional area of this fluid that is flown out of this window should be the same as that of the window. So this has to be 2 meters square and this has to be 10 meter because we are talking about 1 second. So quantity of flow would mean the volume that has flown out of the window per second. So we are essentially trying to calculate the volume of this liquid that has flown. And this seems to me a cuboid. So the volume here would be 10 into 20 per second. So this is meter cube. So this is 20 meter cube per second that has flown out of this window. Let's relate this to electric flux. So if we look at these numbers, I can clearly see that the quantity of flow is 10, which is nothing but the velocity with which the fluid is crossing the window, and this is the area. So imagine if we call this quantity of flow as phi, we represent this with phi. So the quantity of flow would be the product of velocity of the fluid and area through which it is flowing. You have to remember this expression. So we'll be able to relate this to electric flux now. All right, so let's jump to electric flux now. Imagine if we have this area and there are certain field lines that are crossing this area. So let's take the field strength to be E. And the area of this particular plane, this region, is, let's say, A. So let's recall this expression again. So instead of V, we have something very similar to V. We have electric field strength and A comes as is. So the amount of flux is said to be the product of E and A. So the amount or the number of field lines that are crossing this area would be the product of electric field strength and area, EA. So this is called electric flux. It's very similar to fluids, electric flux. Now, it's a very simplistic expression of electric flux. We just have to multiply the electric field strength with area. Now, imagine if we do not have an area that is perpendicular to the field. This area is exactly fitting the electric field lines. Imagine if we have an area which is a little tilted to the field lines. Would the flux remain the same? Let's imagine this area to be like this. Do you think the number of field lines that are crossing this particular area is the same? Maybe not. Because if we talk about this area, I believe some of the field lines would not be able to pass through. So let's say there was a field line like this. So it would have crossed this particular region, but it may not have been able to cross this region. So we can understand from this discussion that this flux that we're talking about certainly depends on E and A, but it somehow also depends on the area that we are taking and its inclination to the field lines. Imagine if we have an area that is, let's say, which is lying like this. So we can clearly see that none of the field lines are passing through this area. So inclination of the area also need to be considered. But this formula, since it's very straightforward and very simplistic, it does not take care of how the area is oriented with the field lines. So we need to have a general formula that explains the orientation part as well. So it's not a difficult thing to understand. We can imagine this area to be a component of this area, the original area. So let's try to explain this again. Let's say we have this area and I'm tilting this area like this, and there's an angle of theta here. So from basic trigonometry, we can understand that if this is a, this has to be a cos theta. So if the area is inclined at a certain angle, we are going to incorporate this cos theta as well. So the final formula for electric flux would be E a cos theta. Whatever is the area, however is the area inclined, this takes care of everything. And we can clearly understand from the previous knowledge of class 11th that this can be written as E dot A. So this is the final expression of electric flux through a given area. And since this is E a cos theta, we can understand that this is a scalar quantity. This is a scalar quantity, as dot product gives a scalar quantity. And let's talk about the units. Electric field has a unit of Newton per coulomb, and this is area is meter square. So we've been able to understand electric flux now.